I want to do a couple of examples from chapter 16 to kind of give you an idea of how we're going to be solving problems in this chapter. I know the notes video didn't really work out. It was way too big and too long. It was about 40 minutes. So this is going to give you really all you needed to know from this chapter, so we can kind of walk through the different types of questions. This is just part one. There's going to be another video that deals with the continuous variables. This one is all about discrete variables. Number 3, it says pick a card, any card. We're basically going to play a game, and it says create a probability model for this outcome. Probability model means I want to create this probability table, right? So x versus p of x. I tend to write mine horizontally. You could also write this vertically. It's up to you. It says that we are going to play a game, and we are basically going to be drawing a card from a deck. We win $0 if we win nothing. And to make sure that really what I'm mapping out here is the amount of money I'm winning. So $0 is the first thing I could win. I could win $5. I could win $10, or I could win an extra 20. Be careful, that's not 20. It's an extra 20 for the ace of clubs. That means just the fact that it's a club, I get $10, right? So an extra 20 would make this $30. Well, don't miss that part. Next, I have to write out the probabilities, right? In this case, we are going to be selecting a red card if I get $0. Red card means I went in and I got 26 out of 52. I'm going to keep this out of 52 because it's going to make it easier for me to check it at the end. For a spade, well, there's 13 of every suit, so 13 out of 52 cards allows me to get $5. $10 is the club. However, one of those clubs gets me the $30, right? So there's only 12 clubs that get me the actual $10 prize, and then the other one, I have 1 out of 52 to get the $30. Now, the rule is when I'm asked to find the expected value, and that's obviously this value right here. Expected is the key word, the amount of money you're going to win. This is expected value. We're going to multiply essentially all the x's times their corresponding probabilities. And it'd look like this. 0 times 26 out of 52. Let's be real clear. That's 0, so I'm probably not going to bother with that one. And 5 times 13 out of 52 plus 10 times 12 out of 52 plus 30 times 1 out of 52. Right? This is what we would consider E of X, the expected value for this scenario. I believe that turns out to be $4.17. I'm not exactly sure about that. I don't have a calculator right here handy with me. Okay, doing this real quick. And so here is, if I play this game a lot, I expect to win about $4.17 on average. Right? That's what you would pay, because I'm going to win a lot of the time. I'm going to win nothing, and that's okay. The probability says that I shouldn't win anything about half the time. And then I have $5, $10, and $30, and those things average out over time to give me that $4.17. Or maybe it's 13 cents, I don't remember. Try it, check it, and see what I get. Okay, the next part asks me, what would I be willing to pay to play the game? You have to take into consideration, what does it mean to play? This is not an opinion. This is something that you have to actually make a decision on. In this example, we are focused on the expected value right here. It means that I would win about this much every time. So I, as a player, would want to make money. I don't want to lose money playing a game. So I'm willing to spend anything less than $4.17. As long as I spend that much money or less, I end up making a profit. If I play exactly that amount, I'm going to make nothing, and it's going to be essentially, if the expected value is the amount of money I'm paying, that's what we would call a fair game. That means that the host as well as the player has the same chance of making or losing money. That's what fair means. The same outcomes for both groups. And that's number 3. Number 5 is it's very similar to question 3. We're going to make that probability table first, right? So we're going to do P of X and X, right? So we'll make that like this. Now be really careful. Actually, I'm going to undo that. we have to be very careful about this one because it's asking a few things. Number one, it asks me to find the number of children they might have, right? So we're going to say X, which is the number of kids, right? I tend to write down what it is I'm counting because it changes. And if I'm counting the wrong thing, I can guarantee you my numbers are going to be off. And so here, we're going to say, well, the number of kids could be, I'm going to have a kid until I have a girl, or we have all 3 boys, right? Or up to 3 kids. So that means that, well, they're going to have at least one kid, right? That would be a girl, okay? If we had 2 kids, that meant I had a boy first and then a girl second. And if we had 3 kids, that meant I had a boy and then a boy and then a girl, but there's also more. I could end up having 3 kids with boy, boy, boy. That's the one people tend to forget about. When you end the scenario, there's generally 2 conditions. I can win by having the girl or just 3 kids in general. They even mentioned that here, even if all are boys. They're kind of giving you that clue that this is going to happen. This part's easy. I'm going to have equal chances of having a kid, a boy or a girl, so that we know the probabilities are going to be the same. Here's a 0.5 cubed and then 0.5 cubed. Remember, when you're doing a probability table like this, this must add up to 1. Okay, if you add all these together, you find out that it definitely gets 1. Okay, it says find the expected number of children, right? Well, we can do that. Another way to do this, I know that we did it by hand in question 3. Another way to do this, we're going to do this. If you want to try this, L1, I'm going to put all of my X values. In L2, we're going to put all of my probability values, right? And then what we're going to do is we're going to go to, let me give you the keystrokes. It would be stat, then it's going to be write, and then it's going to be enter. That gives you one variable stats. Okay, this is what you're going to enter into that L1 or your list. That first value, we're going to put our X values. In this case, we left it in L1. If you didn't use L1, press second and then 1 through 6 on your keypad. That could select a different list. The next one is your frequency list. This is, in this case, we're using relative frequency, which is probability. This is an L2. So press second 2 if that's not already selected. And then you hit enter or calculate to make it crunch the numbers. You are looking for X bar. This is my, in this example, this is what we would call expected value. Really, that's what we consider our mean in this problem. And then, of course, at the bottom, this isn't necessary for this problem, but the sigma is essentially what we call standard deviation. Okay? In other questions, you may need that. In this question, I don't really have to find it. But the expected number of children would be equal to 1.875. Actually, it is not 875, just 1.75. Okay. In the next question, it says find the expected number of boys they have. Well, I'm going to kind of come down here, and I'm going to add a second variable. Well, if I'm counting out, I wrote down which ones were happening on the top. So 0, then I had 1 boy, then I had 2 boys, and then 3 boys. Now, to be really honest, this is really easy. I have a new set of X values, but the probabilities remain the same because I'm still having the same number of children. So those probabilities won't change. So how we can kind of go back and calculate this part, I'm going to do L1 as my Y values, and I'm going to keep L2 the same as my probabilities, right? So I'm going to go back in there, recalculate that. You're going to find the expected value for the number of kids, or sorry, the number of boys, we'll say that is expected value for Y, is 0.875. That's what I was getting from there. And that's how you'd find those two problems. Question number 6. You need to pay attention to this one. This is a great question. It brings together a lot of different aspects of this chapter, and it's kind of tricky. So we're going to start out by, and anytime it asks me to make a probability, if it asks me to talk about finding an expected value, then I'm going to make this table. So x and p of x. I'm also going to put down darts. Okay. In this example, it asked me 3 questions, right? And it says, make a table, then what's the expected number of darts, then what's the expected payout, right? And so here we're talking about the dollars for X, but be careful. Anytime that you have something that talks about you have to pay, it costs to play the game, this is something that we're going to be able to, or we're going to have to keep in consideration when I'm talking about winning prizes. So really, for example, for the first dart, I'm really only going to win $95. It's a net profit because I spent $5 for the dart and they gave me $100 to win the game. That means I'm really only going to have $95. Okay? So how this works out is I'm going to kind of walk my way down. If I have to buy 2 darts, I'm only going to win $90, and then it's going to be 85. That will be for 3 darts. And then for $80, that would be buying 4. I know that I'm only going to go down to 80 because it says that you're only willing to spend up to $20. That means if the dart costs $5, I'm going to be spending $20 at most. Now, the probability that I win on any try means it's independent. It also means that it's going to be 10% every single time. However, what people tend to forget about is that at this stage, it's not 10% again. Because in order to get to the second dart, something had to happen to the first dart. If I win the first dart, I don't go to the second one. So what we know is that I had to lose. That means there's a 90% chance of missing the balloon times 10% chance of popping the balloon. So 0.9 times 0.1 is where I'm going to get my probability for winning the dart on the second try. Just the same way, 0.9 squared, because I had to miss it twice to pick my third dart up, times 0.1 to pop it on the third try. In the same way, 0.9 cubed times 0.1 is also going to tell me the chance that I pop the balloon on the fourth try. Now, if you're quick, if you're paying attention, if you're checking your work, and you've done this, you know that this doesn't come close to adding up to 1. Right? So, and some of you have already thought about this. There is the other option when I actually lose the entire time, meaning I don't pop it on any dart. So I missed it 4 times. Right? This turns out to be 4 darts as well, because at the end, remember, I can stop, and there's 2 ways I'm going to end up stopping on this game. That's when I miss all 4 darts or I pop the balloon. Well, what happens if you don't pop it, right? Okay, so the question, the second question asked me to find the expected value or expected number of darts. Okay, and here again, we're going to use, I'm going to set this up as L1 is equal to the darts. In L2, we're going to put our probability. Right, and once I do that, I find out that I'm going to use 3.44, approximately 3.44 darts. In the second question, it asked me the probability of how much money would I expect to win in this problem. Well, I'm going to use, in this case, L1 is going to be my X values. In this case, it would be the dollars. And then L2 is still my probability, P of X. That doesn't change. Okay, I'm going to type this in. I'm going to work it out. It's going to turn out I'm going to get $17.20. And that's pretty much how you do this question. Okay, the tricky part, so let's revisit those. Number 1, you got to remember that you have multiple things happening. Because they're independent, I can just multiply all of their probabilities together. So I have to consider what's going on. How did I get to dart 2? How did I get to dart 3? What events? There's 3 darts. There's 3 events happening. It was a miss, and then a pop. Right? If I won on dart 3. There's also that one at the bottom. This is what people tend to forget the most. I would miss all 4 darts, meaning I'm going to lose $20, and my values is 0.9 to the 4th power. Still 4 darts, not 5 darts. It's still 4 because there's 2 options that could happen that would end my game in this scenario. And that's question 6. Great question. I would definitely start this over again and try it from the beginning. See if you can work it out by yourself. Question 7 takes a different approach. You have different outcomes, and these outcomes can happen at the same time. So a tree diagram or doesn't really work here. So we're going to use a Venn diagram to start it out. We have the large and we have the small contracts. We know that the large contract is a 30% chance. The small contract is a 60%. I want you to notice I did not put these numbers into my circles because this part of the circle means I only win the large contract, period, not the small. I don't actually know that number yet. This is the same thing here. I don't know these probabilities. This is both. This is only the large. This is only the small. Out here would be losing both of them. So I've got to keep in mind that there is also an outside to these circles, right? But they do tell me this one thing. They tell me that they will be awarded independently, which means I can multiply the probabilities together to figure out the and part. Right? We know that P of A times P of B equals P of A and B. So we know we can do that. 0.3 times 0.6 is equal to 0.18. So here we go, 0.18 there. I'm going to subtract 0.18 from 0.3 and 0.6. We'll get these. 0.12, and then we're going to get 0.42. If I add all those up, subtract it from 1, I'm going to get 72% when I add them all together. Subtract it from 1, I'm going to get 0.28. So that allows me to create this table so I can find the expected amount of profit for a scenario like this, right? So here, I could win $0. I could win $20,000. I could win $50,000, or I could win $70,000 total. Okay, so this would be losing both contracts, meaning that's 0.28. $20,000 is the smaller contract, only that's 0.42. $50,000 is the larger, only that's 0.12. And then 70 is both, that's 0.18. Here again, all 4 sections have to add up to 1, and we know they do. The expected value here, just like last time, you could do it by hand. Probably I would take that right. It's not a whole lot to type in. Or you can type it in your calculator in L1 and L2. But you should get $27,000. There isn't a secondary way to get this incorrectly, and you do get $27,000 as well, but that is not the right way. That's actually just lucky. Anyway, the Venn diagram works out really well when you have an overlapping section where 2 things can happen at the same time. And that way I can go straight into labeling out losing both contracts in the first group, winning only the small, winning only the large, and winning both. That corresponds to each of these pieces inside my Venn diagram. I hope this really helped out. Message me with questions if you have any. See you tomorrow in class.